Hello everyone, my name is Dr. Mo Shiva, Professor of Electrical Engineering at California State University, Fullerton. The purpose of this video is to review mesh analysis. I will do 3 videos for mesh analysis. This is the first of the 3. I'm assuming you're familiar with basics of mesh analysis and we just want to do review examples. To do a quick review, in mesh analysis, we assign mesh currents to each mesh going in the same direction, usually clockwise. Then we apply Kirchhoff's voltage law to each mesh using the mesh currents. Preferred version of Kirchhoff's voltage law is to look at summation of voltage drops around each mesh equal to 0. Voltage drops. If there are current sources, we will use a super mesh that we will review in a future example. For a system with n meshes, mesh analysis results in n equations in n unknown mesh currents. In our first example, we only have resistors and independent voltage sources. This is the simplest possible case for mesh analysis. As I mentioned, we use voltage drop and passive conventions. So for a resistor, current entering positive reference of the voltage results in Ohm's law V equal to Ri, and that really means voltage drop across the resistor is resistance times current entering positive voltage reference of V. Let us write the mesh equations for the circuit. Starting with mesh 1, let us start at lower left corner of the mesh and go in the direction of mesh current so we don't miss any of the elements. First element that we see is the 2 ohm resistor, and voltage across that using current I1 is 2I1, RI1. Again, we are going in the direction of the current, so V is Ri. Next, we see an independent voltage source. We are entering its negative side, so whatever is written there, change the sign of it. So we have -6. We see the 3 ohm resistor. We are interested in branch current going from right to left in the direction of I1, opposite to direction of I3. So that current is I1 minus I3. And finally, we look at the 1 ohm resistor. Current moving in the branch from right to left is in the direction of I1, opposite direction to I2. So it's I1 minus I2 equal to 0. Let's do the same thing for mesh 2. Starting at the lower left corner, first term that we see is voltage of the independent voltage source. We are entering its negative side, so -9. For 1 ohm resistor, we have 1 times. We are moving in the direction of the mesh current, in other words, I2. So we're looking at a resistor with a current moving from left to right. So in the direction of the I2, opposite direction to I1. So we have I2 minus I1. Next, we're looking at a 1 ohm resistor in the direction of I2. So current in the branch is I2 minus I3. And finally, we have a 2 ohm resistor, so plus 2 I2 equal to 0. Mesh 3, starting at lower left corner and moving in the direction of I3. Here is that Vx with a negative sign down below, and that sometimes is a source of mistake. Remember, we are moving in the direction of the current, so that negative has nothing to do with us. We are moving up. We are interested in branch current going up in the direction of I3, opposite direction to I2. So practically forget that. So what we have there is I3 positive, I3 minus I2. Next term plus 3 in the direction of I3, opposite to I1. We see the independent source going clockwise. We are entering its plus, so don't change the sign, it's just positive 4. Plus I3 for the last term equal to 0. Advantage of looking at voltage drops in the direction of mesh currents is, for mesh 1, if you want to quickly check for a sign mistake, we should always have positive I1 or positive I1 minus another current. So it's always positive I1 for mesh 1. Same thing for mesh 2. For mesh 2, we should get positive I2 or positive I2 minus another mesh current. So that makes checking for a sign mistake pretty easy. Voltage drop in the direction of mesh current. So here, if we had made a mistake and we had by mistake written this as I2 minus I3, at this point we can quickly check for a sign mistake, and we know in mesh 3 it should be positive I3, so we would correct that. Let us simplify these equations. We get 6I1 minus I2 minus 3I3 equal to 6. Call this equation 1. And that's again for mesh 1. Second equation gives us negative I1 plus 4I2 minus I3 equal to 9. That's equation 2. And last equation gives us negative 3I1 minus I2 plus 5I3 equal to negative 4. And call this equation 3. Some books talk about writing these equations in the simplified form from the beginning. In other words, if you look at mesh 1, first coefficient 6 is summation of total resistances in mesh 1, and it's positive. Negative 1, the second coefficient, negative 1, is first of all negative, and then it's equal to total resistance common between mesh 1 and 2. And finally, the next coefficient is also negative, and it's 3, and 3 is equal to common resistance between mesh 1 and 3. It works, however, this is a very simple case. When we add dependent sources, current sources, and whatnot, this doesn't really work. So it is there. However, get used to writing the equations the way we have them right here. Simplify and then solve. Check for a sign mistake, then simplify and solve. Solving three equations in three unknowns, there are different ways of doing it. You can use matrices, we can use elimination of variables, substitution for one variable in terms of the other ones. We can use a Cramer's rule. If we want to look at the same equation in matrix form, we get matrix A times vector I equal to vector B. And that gives us 6, -1, -3, -1, 4, -1, -3, -1, 5 times I1, I2, I3 equal to 6, 9, and -4. And we notice that coefficients matrix has some properties. First of all numbers on the main diagonal are positive. Second, all off-diagonal numbers are negative. And finally, it's symmetric with respect to main diagonal. A lot of books put a lot of emphasis on this, but these are really not that important. We call that resistance matrix. This happens if we only have resistors plus independent voltage sources. Otherwise, we will not have those properties. Solving the three equations, any method is fine. I generally like elimination of variables. We notice that coefficient of I1 is 6 in the first equation and -1 in the second equation. So if we add first equation plus 6 times second equation, we eliminate I1. Similarly, if we add first equation to twice of the third equation, we will eliminate I1. So let's do that. So look at equation 1 and add to it 6 times equation 2. That gives us 23I2 minus 9I3 equal to 60. And then take equation 1 and add to it 2 times equation 3. And that gives us -3I2 plus 7I3 equal to -2. From this equation, we can find I2. In terms of I3, and substitute that in the previous equation. So we get 23I2 minus 9I3 equal to 60. One unknown, just solve that and we find I3 equal to 1 amp. Let's substitute that back in equation 4. I2 becomes 7I3, 7 times 1 plus 2 over 3 equal to 3 amps. And finally, we can go back to equation 1 here. Equation 2 here is better because coefficient of I1 is just -1. Let's use that to find I1. So using equation 2, I1 is for I2 minus I3 minus 9 and results in 2 amps. So we have the mesh current. The other unknown of the problem was Vx. Vx is across the 1 ohm resistor. So to find it, we have to multiply 1 by the current entering positive of Vx. Current going down in the branch is in the direction of I2, opposite direction to I3. So Vx is 1 times I2 minus I3. As I said, for this problem, the circuit is very simple. In other words, we only have resistors and independent sources. We can add other types of sources to this, especially current sources. If you have current sources, we should use a supermesh. So look at this next 2 examples, the next 2 videos for mesh analysis to get more familiar with the way we do mesh analysis and solve problems for mesh currents. Having mesh currents, voltages, powers, everything else is easy to find.